So this was for self-driving cars, and self-driving cars are actually robots, and their job is much simpler than the job of a robot, because the job of a self-driving car is just to keep the lane, press the pedal, stop, uh, be careful with the pedestrians, park, not park. So these are a finite set of outcomes that could happen. They are of higher risk because you're playing with the lives of humans, the passengers, and the pedestrians. But in terms of complications, it's much easier as a problem than dealing with actual robots. So this is what we want to do now. And what are the tasks? For instance, a task could be of a robot working at your home, could be inserting a block into a shape sorting cube. So take that block, put it in the shape sorting cube, screwing a cap onto a bottle, like what you see in this image, fitting the claw of a toy hammer under a nail. So this is what is happening here. And placing a coat hanger on a rack, like what you see here. These are the images from the perspective of the robot. So this is what the robot sees. It sees its own arm, it sees the hanger, it sees this image. But what we actually see is this. So this is the actual robot. This is a PR2 robot. And if you put everything in one image, this is what we are seeing, and this is what the robot is seeing. So this is the field of view of the robot. What do we want to do? We want to do this. So a diverse set of actions. So what I want you to do is click on that link and watch it. It's a video explaining the same topic that I just explained. So I want you to go through that. But let's go through the math or the methodology behind this. You want to have a policy, and your policy should be based on your observations. And the observations are these images, red, green, blue images, and your actions, because these guys are coming from the control theory perspective. They are not calling that A, they're calling that U. So this is just a different notation. Observation, actions. And this is where your neural network is going to be. Like any other reinforcement learning algorithm, the question is, how are you going to train your policy? What is your loss function? But here, because these are real robots, you are collecting real data. These are not simulated data. So you have to work in your lab, work with this robot, and then collect data from a physical robot. So these are not simulations anymore. So you have to be able to work with smaller size data. So the size of the data matters. You cannot play your Atari game forever. So you have to be data efficient or sample efficient. And the other one is you are not seeing your states. You're only seeing observations. So you want to work only with images. As I mentioned, UT is your action, which could be in the form of motor torques. These are the commands at the joints. And then the observations are these images. During training, we have access to the state of the system. But during inference, you don't have access. The only observations that you have are your images. So the robot should be able to work with the images. During training, it's okay if you want to use your states. And what are your states? These are the joint angles of the robot, positions of the objects in your environment. And if those objects are moving, your robot should be able to work with those objects as well, with those movements, should be able to adjust itself. What neural network are you going to use? This is your policy neural network. It's going to take as input a red, green, blue image. It's going to do some convolutions. The first convolution has a stride of 2. The rest of them has a stride of 1. There is no padding going on. Because there is no padding, the sizes of your images are going to shrink slightly. Why are you shrinking the sizes slightly? Because you don't want to lose the information of the locations. So you don't want to lose the information of where this sorting cube or shape sorting cube is located in your image, because those locations are important. You want to take that object and insert it here. So the locations matter. That's why you are not doing any pulling, and you are not shrinking the sizes of your images by striding. And that's exactly the reason that you're doing this step. This step is different from any other convolution that we saw before. What are you doing here? You put a softmax It's a spatial softmax per each channel. So these are going to be independent per channel. So let's focus on only one channel. The same thing is going to happen for the other channels. You're putting a softmax on the values that are coming out of your neural network at this stage. And the softmax is going to focus on one point, and it's going to make the other terms go to zero or be closer to zero. And in the end, if you add up these pixels or these pixel values, they're going to add up to one. So that's what your softmax is doing. Now you take that softmax, and you need this because, again, you need to know the locations. You don't want to lose the information that are really important to you, the locations. Where are you going to insert your stuff? You take that softmax and you multiply it by the x coordinate and the y coordinate in your image. So that's your x coordinate of this pixel. That's the y coordinate of this pixel in the original image. And that's why these 32 channels are going to end up being 64, because they have x coordinate, they have y coordinate. These 64, in addition to your robot configuration, I don't know, the angles, etc., because the robot is seeing its own hand. So it has its own information. You push them through a couple of fully connected, and then in the end, you get 7 outputs. And these are the motor torques of what you want to do. So that's your policy. The question is, how on earth are you going to train that while being data efficient? A little bit of the background. This is a finite horizon episodic problem. This is episodic because 1 episode, 2 episode, etc. There is some state dynamics that you are not assuming to be known. Given the state, given the actions that you took, you're going to go to the next state. You have some observations. Given the state, you have some image that the robot is going to see. This one you don't assume to be known as well. Your policy as a function of xt, as a function of your states, because your policy, this is where your neural network is, from the space of images to actions, you have to integrate out those images. Okay, so far so good. So this is just notation. And this is just a distinction that we have to make. Observations versus states. This is where your neural network is. And this guy we don't assume to be known. And then there are some trajectories. You're in state 1, you took action 1, state 2, action 2, etc. That's going to give you a trajectory, and you can put a probability on that based on your policy and your transition and using the chain rule for probabilities. And you also have a cost function. You want to minimize the cost. Okay. What do you want to do in the end? This is our final objective. You want to minimize your cost with respect to the parameters of your neural network, of your policy. So there is this nice trick. Because you want to be data efficient, you are making this trick. And because you don't observe your state, your neural network doesn't observe the state. It only needs to make decision based on the observations, based on red, green, blue images. You're going to do guided policy. What is that? You're going to say, rather than doing my expectation with respect to the actual policy, you're going to seek help from another policy or another distribution over trajectories. Rather than using this distribution over trajectories, you're going to use this other distribution over trajectories under the condition that this other distribution should be equal to the distribution that is going to result from the policy, from where you have your neural network. So now you can divide your problem into 2 steps. And pi tau, you call it guiding distribution. You divide it into 2 steps. First, you optimize your loss with respect to this p, and then you do a simple regression. You say that my parameters of the neural network should match this p, the helper. So you keep alternating. So this is called alternating direction. Method of multipliers. So you change this constraint optimization problem and you put a multiplier on that. So far, so good. But what is this and why is it helpful? Because you can make very simple assumptions on that. So this is a local policy. It is able to look at your states. It doesn't have to look at your observations. So it's going to know during training, it's going to know the state. It's going to know xt. And it's just a linear. It's locally linear. It's local because k is depending on time. And then at the same time, you can model your environment locally. You can model this transition probability. Again, a linear and some variance. It turns out that this is very easy and data efficient to estimate these. And you can, because this is very similar to linear regression. So it's nothing more than that. So it's very easy to estimate K, CT, F, and capital F. So you first estimate those. And during training, you know your XT and you're fine. You are doing your training. During inference, the network is trained. The neural network can look at pure images. It doesn't need to know your state because your neural network is here. And during inference, while your robot is working in the environment, like putting the cap on this bottle, it's going to look at these images only. I think I'm going to stop here and let you guys ask questions. And for those of you who want to leave, you can leave.
So to make sure I understand this, during training, we have access to the physical location of the bottle and the physical location of the hammer and the different objects. And then we can use those as inputs for this guiding distribution. And then our neural distribution is just trained to match whatever outputs that guiding distribution generates using inputs or using images as inputs instead.
Yes, exactly.
Okay.
And why is it possible? Because as soon as you know your XT and you're in the physical environment, you're going to know what image is going to correspond to that.
Yeah.
So an image is going to come out. And then your neural network is going to take that image and it's going to give you an action.
Mm-hmm.
This part is a simple regression, or you can minimize the KL divergence between these two because they are distributions. And the other part is very easy to optimize because these are very easy models. These are simple models. We can actually know the analytical form for your K.
Mm-hmm.
Okay, so right away you get your K, small k, this is the bias and CT.
Mm-hmm.
There is no optimization going on there. You just get it for free.
What is that script N notation for? Is that the normal distribution or is that just saying some network?
Yes, so this is normal distribution with this mean and that variance. So you can make the same assumption for your policy. If an image goes in, it's going to give you some mean and some variance because these are continuous action spaces. You're changing the motor torques.
Yeah, that makes perfect sense. The last question is what did they use for these loss functions, or I guess cost functions, the little L?
So they are going to be when this cube, that depends on the problem. So that's why I'm being a little bit vague there. So for that, you need to read the paper. Actually, it's in the appendix of the paper. But for instance, for this problem, it could be the distance between the pixels of this cube here and the pixels of this guy. So it's going to be the distance between the two.
Do they consider penalizing things like sporadic motion and high speed motion and that kind of stuff? Or is it all just based on getting the cube into the hole?
It's based on getting the cube into the hole.
Okay.
That's it.
Cool.
Yep. And the other cool thing is that, yes, these are linear models, but they are locally linear. So they are really powerful if you think about them in that way, because they are time dependent. So it's not at all a bottleneck. They can give you very good policies and model your environment pretty good.
Quick question. I think maybe I missed that part, but I believe you were saying that we're not reducing the original size of the image because we want to keep the location, but it seems like we're going from 240 by 240 to 117 by 117.
Yes, that's the only part that you're reducing. And
So
that's
then-
only for computational reasons. And
Makes
that's
sense.
not bad. It's just 4 pixels are going to collapse into 1 pixel.
Right. No, that makes sense. But then I'm getting confused on the last part that we're using the softmax and multiplying by the x and y of the original image, because if we're reducing it, we should have 2 x's and 2 y's, if that makes sense.
Yeah, so you just pick the center.
Okay.
So you're right. 4 pixels here are going to correspond to 1 pixel in that image.
Right.
And then you take the center, the coordinates of the center.
Okay. That makes much more sense now.
When I said you are not reducing the size of the image, if you remember, whenever you are doing convolutions and your task is classification, you start with 3 channels and high resolution, but then you keep shrinking the resolution and increasing the number of channels. But here you're not doing that.
Right. Yeah. My only confusion was the last part about the x and y, because we had a multiple of them.
Yes.
Cool.